Do you have thousands of devices out in the field and need an easy way to observe how they're performing in real time, then debug any issues and correct them with over-the-air updates? You need Memfault, and getting it set up with embedded Linux is as easy as pie. Raspberry Pi.
Hey, it's Eamon with ipXchange, and I'm coming at you with our third interview with Memfault. This time I'm joined with Pat Wolfe for another practical demonstration with a Raspberry Pi. So if you haven't seen any of the other interviews in this series, the first one I did was with Gillian, who's a firmware engineer, and she basically explained what Memfault's all about and took us through a demo of the observability platform, kind of in the MCU type environment. Then I had a discussion with the CEO, Francois, and we had this amazing conversation about building versus buying versus blending a solution for observability. So we're going to continue this discussion with Pat. So first off, thank you very much for joining us today. And if you can briefly introduce yourself, what you do at Memfault, and for the third time, let's get a definition of observability for IoT.
Sounds good. Yeah. So I'm Pat. I'm a Linux solutions architect here at Memfault. And what that means is I split my time between two kind of distinct responsibilities, one of which is building Memfault D, which is our Linux agent that will run on Linux devices, collect data, send it to Memfault in a very much software engineering capacity. And then I spend the other half of my time working with both prospects and customers to kind of solution around their devices and see how we can best help them observe the health of their fleet. So, yeah, and then I have been with Memfault for about 10 months and based on the New York City office. And you asked for a definition of observability for IoT.
Indeed.
It is taking the concepts that have been prevalent in the cloud space for a while now of observing software in production and monitoring it for regressions or crashes, and then taking that to IoT space, which is obviously a very different domain in terms of the resources available on the device, the bandwidth of those devices. So we've taken a lot of care to build a solution that can still provide a lot of the insights that cloud developers have been using to make decisions about their software for years, but for embedded developers.
Nice. And I think it's also worth just asking you, because obviously Gillian showed me the MCU type environment for Memfault. What are the different insights, if there are any, that you might use for a Linux environment compared to a real-time operating system, for example?
Yeah. So I would say the biggest difference is that there's a much strong, like the process abstraction is obviously much stronger when working with a Linux system than bare metal or even RTOS, right? So whereas on the RTOS, a lot of the monitoring was around the system as a whole, while we totally monitor the system, the Linux system for metrics, as in like the CPU utilization or the memory usage, our crash monitoring is very much based around processes crashing rather than the whole device crashing, right? So if you have a program that is responsible for one piece of your device's functionality and that crashes, that's what Memfault is going to track rather than with like firmware, right? The whole thing might reboot or hit a fault. So that's a major difference. But at a high level, conceptually, they're very similar. They have the same three pillars of monitoring, debugging, and OTA, and there's a lot of overlap in terms of how it's presented. So, yeah.
Cool. So what are you going to show us today? Can you outline what this demonstration is going to be? And I'll admit to everyone, I'm going in pretty much blind on this. So I'm very excited to see where this goes.
Yeah, so I brought a Raspberry Pi with me today. I have it here in the office. And what we're going to do is take this pretty much fresh Raspberry Pi, install Memfault D on it, and watch data come in. That data is going to be some metrics. Both we'll take a look at system metrics as well as the kind of custom application-specific metrics that users can instrument their software with, logs. And then finally, we'll show how Memfault can capture a crash that occurs in a process on the device and then send it up, give us the ability to analyze it after that crash has occurred and understand what line of code did things go wrong on. So, yeah.
Nice. And just to clarify for our audience, what is the setup for this? Is it, I guess you've got Raspberry Pi and your laptop, or is there anything else involved?
No, so I've got a Raspberry Pi. This is just running Raspbian, and then I have SSH access to it via my laptop.
Okay.
So we're going to be looking at a shell on my laptop, but it's remoted in to the Raspberry Pi.
Okay, cool. So I think the first stage of this is installing Memfault on the Raspberry Pi. So take me through it, and I'll ask cool questions along the way.
Sounds good. Please do. Yeah. So we're going to just take a look at the project I have set up in Memfault. And this is what you would see if you registered for the platform. There's an option to select which like class of device you're working with. So whether it's a microcontroller, an Android device, or a Linux device. Obviously for this, I selected Linux. And then we're taken to this page where there's no data yet, right? And that's what we're going to get or solve. And this time we're going to add some data and hopefully see a lot of these pop up with some interesting charts. So the first thing we can do is go to this setup project button, and that'll take us to a page where we can install Memfault D on our device with this one-liner command, right? So what this is going to do is pull, and I just copied that to my clipboard. It's going to pull some pre-built binary of Memfault D that we're hosting on GitHub. It's just attached to the Memfault D GitHub repository as a release. It's going to pull it straight from there for the architecture your device is running on, and then install it into the system, set up a base configuration that'll collect some metrics, and then start Memfault D, right? So it should be very straightforward. All you need to do is paste this command into your terminal, and your device will be up and running with Memfault. This is not the only way you can get Memfault on your device, right? Like I said, we make the source code publicly available on our GitHub. It's in the Memfault/Memfault D repository. You could cross-compile or compile that yourself and put it on your device. We also have a Yocto layer. So if you are using Yocto to build a custom Linux distro for your device, you can pull in meta Memfault, and it's pretty easy to go from that point to just adding the Memfault D recipe. So there's a few different ways you can pull it in. This is kind of the fastest one for quick evaluation, especially one-off on a particular device.
Cool.
So I'm going to switch my screen share now that I copied that to my clipboard to the shell on the Raspberry Pi. And so you see we're logged in as Memfault on the New York City Office Pi. I'm going to copy in that command and then execute it. And so we're prompted to enter an ID for this device. I'm going to call this IPX demo.
Nice, thank you.
Yeah. And so that needs to be a unique identifier, which for a fleet of one device, which is what we're bringing into this project, is really simple, right? But you maybe had hundreds or thousands or even dozens of devices. What we commonly see users do is use like a serial number or UUID so that each device has a unique ID when it reports into Memfault. Calling this IPX demo will make it really easy to match what we see on the devices page to the device we're looking at right now. But generally, you would not have a custom ID per device.
Cool. And just to clarify for our audience, this is actually running. This isn't kind of a fake demo environment. This is really using the platform.
Right here. Yeah. So what this did, we could see the step-by-step output from the installer script, right? We downloaded the binary from our GitHub releases page, installed it into /user/bin, created a systemd service and started that, and then waited about, I think that the sleep is like for 30 seconds. And what that does is give the Memfault D program a chance to collect data from the system. So we'll pull some readings on what's the average CPU utilization, what is the memory usage, and then take all that and sync it up to Memfault. So I'm doing a lot of switching here, but let's go back to the app and take a look at what's in our project now. Before it was no data.
Within the app, you can set the interval by which it reports.
Yep. So generally, devices will report data in an hourly cadence, right? So it'll collect readings over an hour. And those readings are going to be collected at a much higher frequency generally, right? So every 10 seconds, check, how utilized is the CPU? And then those will be aggregated, whether that is summed together or averaged together over the course of that interval. And then finally, kind of put like serialized together and sent up to Memfault. And there's a few reasons for this. One is a lot of our customers are concerned about how much bandwidth their device might use, right? So if we were sending a reading about the CPU utilization every second, for customers who are using cellular connectivity to connect their devices to the internet, that could get really expensive or even use up their whole data plan just to send, right? Like we want to be an unintrusive tool for observing your devices and not become something that you need to like observe because it's causing a problem. So that gives us a lot of flexibility to work with customers who are constrained, but still want insights from data that's collected more frequently than every hour.
Cool.
So I'm going to, like I said, screen share the app now. And so I've just pulled up the processing log, and this is a tool that's really useful that our engineering team has built that basically just lets you look at the data that's come into a specific project. So we're in this IPX Linux demo project, and it seems like we've gotten a few data points from this IPX demo device. So let's take a look at this, and we can see that this is a Debian, or a device running Debian version 12. That's in line with the Raspbian version I've flashed on this device. And then we can see some metrics that got reported in those over those 30 seconds that we kind of let Memfault run before syncing.
Okay.
And so we can see, let me move this over, right? We have a CPU idle percentage of like it's in the high 99%, right? That's because our Raspberry Pi is not really doing that much besides running Memfault, right? And hey, that's good news though, is that running Memfault clearly does not use a lot of CPU, right? Because it's not like we saw this like drop down to 80% because Memfault is using 20% of the CPU. And then we can also see memory. This is one of my favorite ones because if you see the free memory over time start to trend downward and used memory start to trend upward, that's a big red flag that, hey, there might be a program leaking memory on the system, right? So when you see those stabilize, that just gives me a nice warm and fuzzy feeling that there's no memory leaks. And we can see a few other system metrics like disk operations and networking interfaces. The Raspberry Pi is connected to the internet over Wi-Fi right now, right? So we can see that we're receiving and sending traffic on the Wi-Fi interface on the device. And this is all
so that's the RX and the TX on the...
Exactly, it's RX and TX traffic on WLAN 0, which is going to be Wi-Fi. We can see Ethernet, right? I don't have it plugged in, so that's just going to be 0. So this is all, just from downloading Memfault and letting it run. We collect these insights about the system. I think something else that is likely really interesting for customers is understanding how their applications are behaving, right? And so we have a second classification of metrics, which are like custom application metrics, which can be reported from various processes on the system using the statsd protocol. If you're not familiar with statsd, it's a really simple protocol where you send small UDP datagrams to a statsd server. Memfault has a statsd server built in. So if you're running Memfault you actually already have a statsd server running on your system because it can act as one. And those datagrams basically just represent metric readings. So in the same way that I mentioned, Memfault will collect metric readings from the system, like the CPU utilization, memory usage, every n seconds. The default configuration is 10, and then aggregate them together. You can send a bunch of statsd readings for a specific metric to Memfault, and it will aggregate them together and then send it up at the upload interval. So I'm actually going to quickly do a demo of that using a cool little bash trick. So we can go over here. We're back to our shell on the Raspberry Pi. Cool. And so what I can do is echo, and this will now go into the format of a statsd datagram. Let's call this IPX demo counter. And we'll give this a value of 1 and a type of counter. And there's a few different types of metrics in statsd. Basically, what the type determines is how it should be aggregated. As in, like with counters, they're summed together. We have an implementation of a histogram metric that is averaged together. And then there's a gauge metric where it stores the most recent value over an interval. So counters are really simple, right? We just add all the values together. So let's go with that. And then we're going to send this to /dev udp localhost. And then the default or kind of conventional port to run statsd servers at is 8125. This is also the default configuration for Memfault. It'll start a statsd server at that port, but you can change it if desired. So we'll do this. Oh, what did I do wrong? This should be a slash. There we go. And so we can, to show the aggregation, right? Maybe let's send a second reading, 3.
Okay.
And then we can force a sync. And this is really intended to be used by developers who are testing out an integration of Memfault. We can force a sync with the command Memfault CTL sync. Memfault CTL is a simple API, like a command line API to interact with Memfault. The sync command tells it, hey, don't worry about waiting for the upload interval to expire. Just sync your data right now, which is great for this. Otherwise, this would be another 55 minutes of us chatting, which I'm sure would be great, but maybe it would be a little long. So
I'm assuming, because obviously Memfault for the end user is probably basically invisible, but these are just kind of the things that the developer would use
exactly
from debugging from afar, effectively.
Yep, totally. So I'm going to now do another screen share switch, which I'm now getting really good at switching the window we're sharing. And so we kind of have a bucket of just other metrics. And we can see IPX demo counter has a value of 4 for its most recent report, right? So if you remember, we sent one reading where IPX demo counter was 1, and then sent a second where it was 3. Because it's a counter, we're going to sum those together, and then we get 4 as the resulting value that got sent up to Memfault.
Oh, I see. Okay,
maybe,
cool, nice.
Maybe you care about if your device is a fitness tracker, right? You want to understand how many workouts did a user do in this interval, or how many times did the user try to sync their device to the mobile app that processes their data, something like that, right? So it can be useful to know in a certain duration how many times this event happened.
Cool. What kind of applications might you see that used for embedded Linux? Because I assume most sports trackers are probably going to be MCU based, but I appreciate the example.
No, totally. And these kind of ideas of custom metric and stuff like apply to the MCU space as well. Like you can do this. It's not quite the same path like StatsD, right? But there's also hooks in our SDK to add metrics for basically whatever you want on MCU. But for embedded Linux, like there's a few domains that I feel like embedded Linux is really common in. I see a lot of like video cameras or things like that use embedded Linux. Yeah, like there's the really popular framework GStreamer for Linux that does video processing, or like lets you kind of build your own video processing pipelines. So I think that is really appealing for a lot of teams working on like cameras or other video applications. So cool. That's a big one. Also, it's just very nice to have like the Linux networking stack, right? You don't need to roll your own like CP stack or something, right? Like that is my favorite part working on embedded Linux is like I have libcurl, right? So I never need to worry about that not working. So
actually, just wondering what which Pi is this running on?
This is a Raspberry Pi 4B, and I added a little screen to it that I bought off Amazon, but under the hood or in the case, it's just a Raspberry Pi 4B.
Cool.
Cool. So something else I want to show off that we actually don't need to go back to the Raspberry Pi shell is that we've also this whole time been collecting logs from the device. So what this is going to be is the same output you'd see if you ran like journalctl on the Linux system locally. So Memfault hooks into the system's journal and will actually pull logs from there and then send them up whenever we do that Memfault CTL sync, which we just did a few times. So we have a few different log files here, and we can see logs from when the system was booting up, as well as logs from various services that are running on the system, right? So we have a file system check run by systemd. We've got cron, and then, Now, this is kind of my favorite part of Memfault. I think this is the coolest feature we have, the thing I'm most excited to show today. So we're going to take a look at our crash monitoring. So I am going to now go back to the Raspberry Pi. And so kind of in preparation for this demo, I wrote a simple C program that is just going to cause a segmentation fault, right? So we can take a look at the source code here. And so you can see this is, again, really simple, right? We've got this main function. All it's going to do is call function that crashes and then function that crashes. Going to initialize a null pointer. And then in this printf, it's actually going to dereference that null pointer, right? So if you've ever written C before, you know what this is going to cause, or it's going to seg fault and cause a crash, right? So this is obviously a little bit simple, but I think if you, like I said, have written C in a complicated project, you know how easy it is to get into situations where something like this happens. So I've compiled that here. We can run it, and we'll see, just as expected, segmentation fault, core dumped. And this is when that core gets dumped is where Memfault comes into play, because Memfault D will actually hook into the Linux core dump handler. And so instead of something really common that people have the Linux core dump handler do is just write the core dump to a file on disk. And then after the fact, maybe access the device, pull off the core dump. What we do is first basically do some processing on the core dump to remove memory that is not going to provide debugging signal to the user. This is to make the core dump a lot smaller. If you take that approach that was mentioned and have it dump all the memory to a location on the file system, you can end up with a core dump that is gigabytes large. To go back to what I said about,
you definitely don't want that for cellular.
Yeah, exactly. So we take a more strategic approach, and by default, we'll only capture memory that's on the stack for each thread in the program. And that's really enough, as you'll see, to give us a pretty detailed analysis of the crash. So similar to what I did with the custom metrics, we're going to run a sync, and this will take the core dump that Memfault D captured and then upload it to Memfault where it'll be processed. So that ends the segment we need the Raspberry Pi shell for. And let's go back to our app. And so we can refresh. And here we go. So we see that at 11:41. Or no, wait, that's sorry. We can see at 11:31, Memfault received a core dump from this device. And then, like I said, when we receive a core dump, what we're going to do is process it. And the processed form of a core dump in Memfault is called a trace, right? So the core dump is the raw data that we capture when the crash happens on the device. And then our system produces a trace, which is the processed version that we can analyze in the app. So we can jump into that. Cool. So just as expected, we report a seg fault in the function that crashes function. If you remember, that was the function that actually has the printf with the null pointer dereference. And then we can scroll down and actually, even beyond that, see the lines of code for the stack trace. So on line 11, main function called function that crashes, and then line 5 in function that crashes was the one that had the printf with the null pointer dereference. So this is really the same information you'd get if we maybe received a report from a customer that described this crash. We went through the work of reproducing this crash with a dev device hooked up to a debugger, finally reproduced it, and then ran backtrace in GDB to get this information. We get it all, as soon as the crash happens. We probably are looking at this core dump before the customer even has time to type up the customer support ticket. So this is really powerful. And so we could see logs from the device as well as a few attributes. Something I think can be really helpful is that we can actually see the command that was executed to start the process that crashed. In this case, it's a pretty simple one where we just executed the binary. But if you have a command that maybe runs with a few CLI arguments, right, this could be an indication of an argument that isn't handled properly or something like that. So I think that could be really helpful. And this is I think the coolest part of Memfault is this sort of crash monitoring that gives us the information that it would normally take a full reproduction to get just in the app. So
nice. So I guess we're obviously, it's because you created the crash, we're not going to do an OTA update to fix it. But in the event that that a crash did occur, what would be the next steps after that?
So I think there's a number of steps between 0 and infinity where we actually fix the crash, right? Maybe this line of code it's really obvious why it might crash, or maybe it takes subsequent investigation and kind of diving deeper into the different states the device can get into or the software can get into. But Memfault has a full OTA provider feature set, right? We have the ability to upload OTA payloads and target devices with them. We have a CDN for distributing your like OTA payloads in an efficient and cost-effective manner. And we have the ability to group devices into certain cohorts, a really common one. And those cohorts can be targeted for OTA updates. So a really common one is like dividing devices into a beta cohort and a regular users cohort, and then updating the beta cohort first. Maybe this is something that an issue came up, like this crash may have just occurred in the beta cohort before it rolled out to production or like regular users. And then we'll actually just roll out an update for the beta users so they don't have to deal with this anymore.
Nice. Cool. I would ask stuff to do with the fleet, but we are a fleet of one.
But we can still take a look.
So,
we can search for
what it looks like at that point.
We can search for a device. Maybe we have a few, right? It might be interesting to search for a specific device. And we can take a look at our overview page. So these update every few hours. So because we just added this today, but we can see a breakdown. We have one device. It's running Debian 12. That's 100% of our fleet. So that's pretty straightforward. But something that I do think is pretty cool is we can see on this overview page a list of new issues. So if a crash happens for the first time, it'll be here. This is especially interesting if you're rolling out new software, right? You might care, hey, is a crash that didn't happen on previous software versions seen in this newest issues page, right? So we did, since this project is brand new and this was the first crash, we did just introduce this seg fault in the crasher program. So that'll show up there.
Yeah, and I guess if you had multiple devices with the same crash, it would recognize those as similar events.
Yeah, exactly. That's a great question / like teeing me up. So we have a grouping algorithm that when traces have the same stack trace. So for this one, it was line 5 in a function that crashes, and then line 11 in main. Those will get all grouped together. And then you can know, okay, this crash, maybe, like let's say we were running that crasher program on startup for every device that was on a specific software. We'd see a lot of those crashes, right? And those would all be grouped together. So if we have one crash that we know happens on 3,000 or has happened on 3,000 devices 10,000 times across those 3,000 versus another crash that has happened on 6 devices a dozen times across those, right? Like we know, that the first one is impacting way more users, way more devices in our fleet. Let's prioritize figuring out that one.
Yeah. Cool. Well, is there anything else you'd like to show me within the platform for a Linux environment? But otherwise, I thought it was a really good demo. Really, I didn't actually expect it to be completely real time. So this is excellent.
Definitely caused a lot of anxiety.
One of the nice things about Enterprise.
Real-time demos are always fun. I think that covers the kind of key things you get out of the box with that pre-built installer script. And I definitely would encourage people who have a Linux device, whether it's a Raspberry Pi or an IMX dev kit, or even a desktop machine running Linux, to try it out and see what data they get in the platform. I think it's a great way to see, you can look at screenshots and understand this is what I could see if I instrumented my device, and it's not clear how many steps we need to take or how long is that going to take, right? I think the nice thing about a kind of installer like this is you can see, in a matter of minutes, this is the data I get out of the box. So like I said, definitely encourage people to try it. And we love to kind of, like, a big part of my job is kind of guiding people through evaluating Memfault and if it's the right choice for them and their team as an observability tool. So definitely also feel free to book an appointment or a meeting with us on our website. And it's one of my favorite parts of my job is getting to talk to different teams that work on different devices and understand what they're building, what the hard parts are, what they care about observing. So,
Nice. So just to clarify, what is the best way to do this? Is it to go through the GitHub? Is it to go through the sandbox down, or in this case, is it to go straight to Memfault as a contact?
Yeah. So you can create an account and be taken to the project page, which I showed. And we at the beginning of the video, we went over to that setup project. This is where you can get that command that you can copy and paste into a shell on your device. But I think also, like, if you get to the point that this command is sending interesting data, you're part of a team that's building a device, and you'd like to have this observability in production. We have a sales team that would love to meet with you and talk to you about your device and kind of move forward from there. But yeah,
cool. And in the kind of trial setup, is what kind of number of devices are you allowed to play with?
Cool. At a high level, we'd love for people to try this out, and then if it looks interesting, contact us. We'll meet and talk about what makes sense.
Excellent. Well, thank you so much, Pat, for showing me that demo. I had a lot of fun, and as I said, I'm no expert in Linux, but that actually seemed really simple to set up. So, which is a good sign.
Definitely.
Cool. So yeah, to any of the engineers working out there on Linux-based systems, here's a demo of Memfault for your use cases, and I hope you enjoyed this demo. You enjoyed Pat and I's banter, and look forward to trying it out yourself at some point. So yeah, we've got links to all the places you'll need to go in the full write-up. But again, Pat, thank you very, very much. And yeah, all this Memfault content has been really, really exciting. So I'm looking forward to the next one.
Me too. Yeah, thanks for having me, and thanks for watching. It's great.
Hey, yo, where my engineers at?